Today, we're tackling something that could revolutionize how we classify and process data, learning vector quantization, or LVQ for short. Now, I know what you might be thinking. Another machine learning algorithm? Haven't we already got enough of those? But hold on, this one's different. LVQ takes a fresh approach to classification by using representative vectors rather than storing every single data point like KNN. That means faster processing, less memory usage, and a more intuitive way of recognizing patterns. But before we get too deep, let's set the stage. First, we'll explore why traditional methods like KNN sometimes fall short. Think computational complexity, memory inefficiency, and their sensitivity to irrelevant features. Then we'll see how LVQ flips the script with its winner-takes-all strategy, refining representative vectors over time for improved accuracy. And it doesn't stop there. We'll break down the key components, the best matching unit, BMU, how vectors are adjusted, and the training process that makes LVQ tick. We'll also discuss its advantages, like its robustness against noise, its non-parametric nature, and how it outperforms KNN in handling large datasets. But every silver lining has a cloud, right? LVQ has its own challenges. Choosing the right learning rate, handling high-dimensional data, and the sheer number of iterations needed to get the best results. Don't worry, though. We'll talk about how to fine-tune the model, optimize its learning rate, and even explore dimensionality reduction techniques to make LVQ even more powerful. And just when you think you've got the hang of it, we'll take a step into the real world. LVQ isn't just theory. It's used in speech recognition, medical diagnosis, image classification, and financial forecasting. Think about that for a second. This algorithm isn't just making predictions, it's helping diagnose diseases, transcribe speech, and even detect fraud. Now, if you're wondering where this is all heading, stick with me. Towards the end, we'll compare LVQ with KNN, look at how it can be improved with hybrid models, and even discuss its future, where it fits in with reinforcement learning, explainable AI, and real-time data processing. So, are you ready to rethink how we classify data? Let's jump in. Learning Vector Quantization, LVQ, a powerful yet often overlooked approach to supervise machine learning. Now, you might be wondering, why should I care about LVQ when there are already so many classification algorithms out there? Well, here's the thing. Many traditional methods, like k-nearest neighbors, KNN, rely on storing entire datasets, which isn't just inefficient, it's downright impractical for large-scale applications. Imagine trying to search for a contact in your phone, but instead of a neat, organized list, you had to scroll through every number you've ever saved. Not fun, right? That's the kind of inefficiency we're talking about. This is where LVQ changes the game. Instead of memorizing everything, it identifies the most important patterns and learns from them. It's like having a mental map of the city instead of needing GPS for every single turn. The result? Faster classification, less memory usage, and a model that adapts intelligently to its data. But how exactly does LVQ work? And what makes it different from other classification techniques? Stick with me, because in the next slide, we're going to break down the limitations of KNN, its hidden flaws, the computational headaches it causes, and why LVQ is the smarter, more efficient alternative. You don't want to miss this. 3.21, let's talk about k-nearest neighbors, or KNN for short. Now, don't get me wrong, it's a classic, a staple of machine learning, like the little black dress of classification algorithms. You give it a data set, it memorizes everything, and when a new data point comes in, it finds the k closest neighbors and classifies based on majority vote. Simple, right? Almost too simple. And that's where the problems start. Imagine you're at a party and you want to know if it's a fun crowd or a dull one. Instead of taking in the vibe of the whole room, you awkwardly ask the 5 people nearest to you, "Hey, is this party fun?" If they say yes, you stay. If they say no, you leave. But what if you just happen to ask the 5 quietest people in the room? Or worse, what if you're standing near the snacks and all 5 are just there for the free food? KNN does something similar. It classifies based on proximity without really understanding the bigger picture. One of its biggest weaknesses, it's super sensitive to irrelevant features. Say you're classifying emails as spam or not spam. You train your KNN model on words in the email, but what if there's a weird feature like the font size of the email? If that accidentally influences classification, your model might start thinking all emails with big fonts are spam. Imagine a poor grandma trying to email her grandkids in size 24 Comic Sans straight to the spam folder. And let's not forget the brutal inefficiency of KNN. Every time it needs to classify something, it has to compare the new data point to every single item in the training set. That's like searching for a missing sock by checking every drawer, every closet, and even under the fridge every single time you do laundry. The bigger the data set, the slower it gets. You want real-time predictions? Not with KNN memory usage. Oh boy, KNN has the hoarding tendencies of someone who refuses to delete old emails. It keeps every data point it has ever seen. That might work fine for small datasets, but if you're working with millions of images, documents, or medical records, KNN will eat up memory like a buffet. And trust me, that buffet bill gets expensive. And then there's the whole curse of dimensionality. Sounds like something from a sci-fi movie, right? But it's real. As the number of features in your data increases, the distance calculations in KNN become less meaningful. Think of it like judging a person's personality based on 1 or 2 traits. It kind of makes sense. But if you try to factor in 100 different things, from their favorite pizza topping to how often they floss, you just end up with a mess of meaningless information. KNN struggles in high-dimensional spaces because distances lose their ability to differentiate classes effectively. So, what do? If KNN is like a forgetful detective who needs to check every file before making a decision, we need something smarter, something that doesn't need to remember everything, but still makes sharp, accurate decisions. And that's where Learning Vector Quantization, LVQ, steps in. Instead of hoarding all the data, it identifies only the most relevant pieces and refines them over time. It's lean, it's fast, and it doesn't get bogged down by unnecessary details. So how does LVQ actually work? What's this winner-takes-all strategy, and why does it sound like something from a casino? Let's break it down in the next slide. Trust me, you'll want to see this. Now that we've exposed KNN's flaws, let's talk about a smarter way to classify data, Learning Vector Quantization, LVQ. And to really understand how LVQ works, we need to talk about its secret weapon, the winner-takes-all strategy. Sounds intense, right? Like a high-stakes poker game or a reality show finale. But trust me, it's simpler than it sounds and way more efficient than KNN. Imagine you're playing a game of Find the Best Representative. You're in a room full of different groups of people. Some love rock music, others are all about jazz, and a few are hardcore classical fans. Now, instead of memorizing every single person's name, favorite band, and favorite song, which would be the KNN approach, you pick one person from each group to act as the representative. Whenever someone new walks in, they simply check which representative they're closest to and get classified accordingly. That's exactly how LVQ works. Instead of storing every single data point, it identifies a few representative vectors, also known as prototypes, that summarize the key characteristics of different classes. Think of them as class champions, the best examples of what each category should look like. And this is where the winner-takes-all part comes in. Here's what happens when a new data point enters the system. Step 1. LVQ finds the best matching unit, BMU, the prototype that's closest to the incoming data point. It's like picking the friend whose music taste is most similar to yours. If you love indie rock, you're not going to end up in the classical group. You'll naturally gravitate toward the indie fan. Step 2, adjustment. Instead of just classifying and calling it a day, LVQ learns and improves over time. If the BMU correctly represents the new data point, it moves even closer to it. If it misclassifies, it moves away, refining itself with each new example. It's like a self-improving group leader, getting better at representing their crowd every time they meet someone new. Over time, this process fine-tunes the prototypes so they become more accurate and representative of their class. The result? LVQ doesn't just memorize the data, it understands it, adapting as it learns. Now, this is where it gets really cool. Unlike KNN, which slows down as datasets grow, LVQ becomes more efficient the more it learns. Instead of sifting through thousands of data points every time, it quickly compares new inputs to just a handful of well-trained prototypes. Imagine being able to identify the best pizza place in town, not by reading every single Yelp review, but by just asking 3 food critics who have already done the work. That's LVQ. And this is just the beginning. We've talked about the winner-takes-all approach, but what makes LVQ really shine is its iterative learning process, the way it gradually refines its understanding of data, improving its classification accuracy over time. So, how does this training process actually work? How does LVQ become so precise? Let's break it down in the next slide. You're going to love this part. Let's zoom in on the real heroes of learning vector quantization, the representative vectors. These are the backbone of LVQ, the MVPs of classification. Forget about storing every single data point like KNN does. LVQ is all about efficiency and intelligence. It picks a select few prototypes that best represent different classes and continuously improves them. Think of it like training a small group of expert chefs instead of hiring an entire city of cooks. The goal? Fewer but smarter representatives. Imagine you're running a massive company and you need to know what your employees think about a new policy. You could individually interview every single worker. Sounds exhausting, right? Or you could select a few team leaders who represent their departments. If they give feedback that aligns with their team, great. But if their views don't reflect reality, you adjust, swap, or retrain them. That's exactly what LVQ does. Here's how it works. Instead of memorizing every data point like KNN, LVQ places representative vectors in the input space. These prototypes don't start off perfect. They're randomly placed at first, just like hiring fresh recruits. But as training goes on, they get refined and repositioned to better capture the true structure of the data. So, when a new input comes in, LVQ doesn't waste time checking every single stored sample. Instead, it finds the closest representative vector, the best matching unit, BMU, and classifies accordingly. If the BMU is a good fit, it moves even closer to the input. If not, it self-corrects, shifting away and refining its position. The result, over time, these representative vectors become highly optimized and serve as a compressed, super efficient version of the dataset. This method is what makes LVQ so much faster than KNN. Instead of relying on brute force to compare everything, it intelligently learns what truly matters. It's like training a small team of top-tier employees who can handle complex tasks without needing constant micromanagement. And here's the best part. LVQ can adapt to changing data. Unlike static models, it repositions representative vectors over time, keeping them relevant and up to date. This is why LVQ works so well in fields like medical diagnostics, speech recognition, and financial predictions, areas where patterns evolve and flexibility is crucial. But how does LVQ actually train these vectors? How does it go from a messy, unorganized start to a well-structured, high-performing model? Well, that's where the real magic happens. In the next slide, we'll break down the step-by-step training process, from initializing prototypes to fine-tuning them through iterative learning. Trust me, this is where LVQ truly shows its brilliance. Here, now things are getting exciting. We've seen how LVQ picks representative vectors instead of hoarding every data point like KNN. But how does it actually train these vectors to become better, smarter, and more accurate over time? Well, buckle up, because this is where LVQ turns from a simple idea into a machine learning powerhouse. Let's imagine you're training for a marathon. You don't just wake up one day and magically know your perfect running pace. At first, you start with random efforts, sometimes running too fast, sometimes too slow, but over time, with training, you adjust, finding the right balance until your pace becomes smooth and efficient. That's exactly how LVQ trains its representative vectors. The process begins with randomly initialized prototype vectors. These are placeholders, just rough estimates of what each class might look like. Think of them as rookie athletes, raw, unpolished, but full of potential. Now let's go step by step through LVQ's training process. First, an input pattern is presented to the model. This is like feeding the system a new piece of data and asking, where do you think this belongs? Next, LVQ identifies the best matching unit, BMU, the prototype vector closest to the input. This is the winner in our winner-takes-all approach. But here's the game changer. Instead of just classifying and moving on, LVQ adjusts the BMU's position. If the BMU correctly represents the input, it moves closer to it, refining itself to become a better match over time. If the BMU misclassifies, it moves away, forcing the system to reorganize and improve its structure. This is what makes LVQ so different from KNN. It's not just storing and retrieving, it's learning and evolving. This process is repeated for multiple training iterations. Each time, the representative vectors shift, fine-tuning themselves until they perfectly distribute across the input space. It's like a group of marathon runners figuring out the best pace, not in one attempt, but through continuous feedback and adjustment. And let's talk about the learning rate, the speed at which LVQ updates its vectors. In the beginning, you want big adjustments. Just like when you first start training, you experiment with different speeds to get a feel for things. But as you improve, adjustments need to be more precise, making small refinements instead of drastic changes. That's why LVQ gradually decreases the learning rate, starting with big moves, then fine-tuning with smaller ones as training progresses. So after all this, what's the end result? Instead of a clunky, memory-hungry model like KNN, we get a lean, adaptive, and highly efficient classification system. LVQ learns which features matter most, organizes them into powerful prototypes, and constantly improves itself with every new data point. But here's the million-dollar question. How does LVQ use these trained vectors to actually classify new data? What happens when a fresh, unseen input arrives? And what role does the best matching unit, BMU, really play in making decisions? That's exactly what we're diving into next, and trust me, this is where LVQ starts flexing its real power. You don't want to miss it. All right, we've talked about how LVQ trains its representative vectors, but now it's time to talk about the real decision maker in this whole process, the best matching unit, or BMU. This is the key player in LVQ's classification process, the one that determines where a new input belongs. And believe it or not, this little algorithmic champion is smarter than you think. Let's break it down with a simple analogy. Imagine you walk into a crowded cafe and you're trying to find a seat. You don't just wander aimlessly. Instead, you scan the room and look for the table that best matches your vibe. Maybe it's a group of people discussing the latest tech trends, or maybe it's the quiet corner where someone's reading a book. The point is, you find the closest match and sit there. That's exactly what the BMU does. It scans all the representative vectors and picks the one closest to the incoming data. But how does it determine what's closest? That's where distance metrics come in. The BMU typically uses Euclidean distance. That's just a fancy way of saying, how far is this input from each prototype? The one with the smallest distance wins. It's like measuring how similar two songs are based on their tempo and melody. The closer they match, the more likely they belong to the same genre. But here's where it gets really clever. The BMU doesn't just classify and move on. It adjusts itself every time it makes a decision. If the BMU correctly classifies an input, it moves even closer to that data, improving its representation over time. If it misclassifies, it shifts away, ensuring that future classifications are more accurate. This is what makes LVQ so powerful. It's constantly learning and refining itself, unlike KNN, which just stores data and never improves. Now, what if you're dealing with complex datasets where Euclidean distance isn't the best fit? No problem. LVQ can adapt and use different distance measures like Manhattan distance or Minkowski distance, depending on the structure of your data. Think of it like changing how you measure similarity. Sometimes straight line distance, Euclidean, works best, and sometimes it's better to count steps along a grid, Manhattan. And here's a fun fact. BMUs aren't just used in LVQ. They're the foundation of many AI models, including self-organizing maps and neural networks. They help systems make fast, intelligent decisions by focusing only on the most relevant features. So, to sum it up, BMU is the brain behind LVQ's classification. It scans, finds the closest prototype, and adjusts itself to become better over time. The result? A machine learning model that doesn't just classify data, it actively improves itself with every new input. But now comes the real question. Why does LVQ outperform KNN in so many real-world applications? Why is it more efficient, more scalable, and better at handling noise? In the next slide, we'll break down the major advantages of LVQ and see how it stacks up against traditional classification methods. Trust me, this is where LVQ really starts to shine. All right, now that we know how LVQ classifies data using the best matching unit, BMU, it's time to answer the big question. Why is LVQ so powerful? What makes it better than traditional classification methods like KNN, and why should you care? Well, here's where things get really interesting. Let's start with efficiency. Remember how KNN is like that one friend who never deletes anything from their phone, storing every single message, photo, and meme? Well, LVQ is the complete opposite. Instead of hoarding data, it learns from it and keeps only the most relevant information. This means faster classification and way less memory usage. If KNN is a cluttered desk buried in paperwork, LVQ is a sleek, well-organized filing system that finds exactly what you need in seconds. And then there's speed. Every time KNN wants to classify a new input, it has to scan the entire dataset. That's like trying to find a book in a massive library without a catalog. Slow, inefficient, and exhausting. LVQ, on the other hand, only compares new inputs to a handful of representative vectors, meaning it gets faster over time instead of slower. Imagine being able to recognize a song just by hearing a few notes instead of listening to the whole track. That's the magic of LVQ. But what about noise and outliers? One of KNN's biggest problems is that it gets easily fooled by irrelevant or misleading data points. If one bad apple sneaks into the dataset, KNN might just assume the whole batch is rotten. LVQ, however, ignores noise by refining its representative vectors over time. It focuses on the big picture, not the outliers. That's why it's used in fields like medical diagnostics, where a few unusual cases shouldn't throw off the entire classification model. Another game changer, LVQ is non-parametric. That means it doesn't assume anything about the data distribution. Unlike some models that need perfectly normal, bell-shaped data distributions, LVQ is like a street-smart detective. It learns patterns on the fly without needing any predefined rules. Whether your data is clean and structured or messy and unpredictable, LVQ adapts. And let's talk real-world applications. LVQ isn't just theory. It's used in speech recognition, image classification, fraud detection, and even financial forecasting. Why? Because it's incredibly scalable and versatile. Imagine training a security system to detect fraudulent credit card transactions. Instead of analyzing millions of past transactions every time, LVQ just learns the patterns of fraud and classifies new transactions instantly. That's speed, efficiency, and intelligence all in one. But of course, no algorithm is perfect. LVQ has some challenges too. It needs careful fine-tuning, and choosing the right learning rate is crucial. If it's too high, the model jumps around without ever settling. Too low, and it learns at a snail's pace. And let's not forget about high-dimensional data. As the number of features increases, LVQ needs more representative vectors to keep up. So, what are these challenges? And more importantly, how can we fix them to make LVQ even better? That's exactly what we'll explore in the next slide. Because understanding an algorithm's weaknesses is just as important as knowing its strengths. Stay tuned. All right, we've seen why LVQ is a game changer, faster, leaner, and smarter than KNN. But let's be real, no algorithm is perfect. LVQ has its own set of challenges, and if you don't handle them properly, things can go south fast. Think of LVQ like a high-performance sports car. It's powerful, but if you don't fine-tune it, it's going to skid off the road. So, what are the bumps in the road when working with LVQ? Let's break them down. First up, sensitivity to the learning rate. If the learning rate is too high, LVQ ends up jumping all over the place, never really settling on the right representative vectors. It's like trying to draw a perfect circle but constantly making huge wild adjustments. On the flip side, if the learning rate is too low, the model learns at a painfully slow pace, like trying to carve a sculpture with a butter knife. You need to find that sweet spot, starting with a higher learning rate for big movements and then gradually decreasing it to fine-tune the details. Next, let's talk about computational complexity. While LVQ is way more efficient than KNN, it's not immune to scaling issues. If your dataset is massive, you need more representative vectors to capture all the patterns, and that increases the training time. Imagine trying to summarize a 1,000-page book with just 3 sentences. You'd need more points to truly represent the data. And here's where things get tricky. High-dimensional data. LVQ, like many machine learning models, struggles when dealing with too many features. This is called the curse of dimensionality. As the number of features grows, the algorithm needs exponentially more representative vectors to maintain accuracy. Think of it like trying to recognize a song, not by the melody, but by analyzing every single note individually. It becomes chaotic and inefficient. Another challenge? Extensive training iterations. Unlike KNN, which just memorizes data, LVQ has to train and refine its representative vectors through multiple passes. This means you can't just plug in data and expect instant results. You need patience and fine-tuning. But here's the upside. Once trained, LVQ is lightning fast. The effort you put into training pays off with rapid classification speeds down the line. Lastly, choosing the right number of representative vectors can be tricky. Too few, and you're oversimplifying the data, leading to misclassifications. Too many, and you're overcomplicating things, slowing down the model without much benefit. It's like picking the right number of team captains in a tournament. You need enough to represent all skill levels, but not so many that it becomes confusing. So, what's the fix? How do we fine-tune LVQ to overcome these hurdles? That's where optimization techniques come in, adjusting the learning rate, implementing dimensionality reduction, and carefully selecting the right number of prototypes. And in the next slide, we're going to dive deep into these game-changing solutions. If you want to get the most out of LVQ, you won't want to miss this. Fine. Now let's talk about one of the most important ingredients in making LVQ work flawlessly, the learning rate. If LVQ is like a professional athlete training for a big competition, then the learning rate is the training intensity. Push too hard and you burn out. Go too easy and you never improve. This is where learning rate decay comes in. A simple but genius trick to make LVQ learn efficiently without losing control. Let's break it down. At the start of training, LVQ needs to make big adjustments. Think of it like sculpting a statue. You start with a chisel, making broad, rough cuts. That's why we begin with a high learning rate, so the model can quickly position the representative vectors in roughly the right spots. But as training progresses, We don't want drastic movements anymore. We need precision. This is where we gradually lower the learning rate, making finer and finer adjustments. Back to the sculpture analogy. After the rough shaping, you switch to fine tools, carefully refining every detail. If we kept the learning rate high, the model would just keep jumping around, never settling down. If we drop it too quickly, the model won't have enough time to reach its optimal state. So how do we actually decay the learning rate? There are a few popular strategies. One is exponential decay, where the learning rate is reduced by a fixed percentage after every few iterations. It's like sharpening a skill. You start off making big improvements, but over time, progress slows as you master the basics. Another approach is step decay, where the learning rate drops at specific milestones. For example, after every 100 iterations. Imagine a personal trainer telling you, all right, we're cutting your workout intensity in half every month to focus on technique. And then there's inverse time decay, where the learning rate shrinks gradually based on a formula tied to the number of iterations. This is useful when you want a smooth, continuous reduction in learning speed. But why does this matter? Because LVQ thrives on balance. Without proper learning rate decay, the model either jumps around aimlessly, high learning rate, or stagnates without improving, low learning rate. By controlling this process, we make sure LVQ learns efficiently, adapts accurately, and avoids overfitting. And speaking of overfitting, that's a major concern in machine learning. If the model memorizes the training data too well, it won't generalize to new data. So how does LVQ handle this? And more importantly, what steps can we take to prevent overfitting and make our model robust? That's exactly what we're tackling in the next slide. Stay with me. This part is crucial. Okay, it's time for the ultimate showdown. Learning Vector Quantization, LVQ, versus K-nearest neighbors, KNN. If you've been following along, you already know that KNN is like that one friend who remembers everything. Every text, every detail, every inside joke. Meanwhile, LVQ is the friend who learns what matters, filters out the noise, and makes smart decisions based on real understanding. But let's go deeper. First off, memory usage. KNN is a hoarder. It keeps every single training sample. That means as your dataset grows, KNN demands more and more storage until it becomes an absolute memory monster. LVQ, on the other hand, is efficient. Instead of remembering everything, it summarizes the dataset using a small number of representative vectors. The result? Way less memory consumption and a much lighter model. Now let's talk classification speed. Every time KNN wants to classify something, it has to compare the new data point to every single stored sample. That's like checking your entire camera roll just to find one specific photo. It's slow and only gets slower as data grows. LVQ? Lightning fast. It only compares the input to a handful of representative vectors. Once trained, LVQ scales beautifully and maintains consistent speed, even with massive datasets. Then there's robustness to noise. KNN is like a detective that takes every witness statement as fact, even if some people are clearly lying. If your dataset has irrelevant or misleading data, KNN can easily be tricked into misclassifications. LVQ, it filters out noise over time by refining its representative vectors, meaning it focuses on real patterns rather than memorizing random details. That's why LVQ shines in real-world applications like medical diagnosis, speech recognition, and fraud detection, where a few bad data points shouldn't throw off the whole system. But what about accuracy? Here's where it gets interesting. If KNN has a huge data set and the right distance metric, it can be very accurate, but at the cost of speed and memory. LVQ, on the other hand, needs proper training and tuning to reach high accuracy. If the learning rate is too high or the number of representative vectors is too low, it might struggle. But once fine-tuned, LVQ delivers competitive accuracy with way more efficiency. And here's a big one, adaptability. KNN doesn't adapt. It just sits there with its massive data set answering queries like a search engine. LVQ, on the other hand, evolves. Over time, its representative vectors improve, making it far better suited for dynamic environments where data patterns change over time. So what's the verdict? If you need simple out-of-the-box accuracy and don't mind the memory and speed trade-offs, KNN might do the trick. But if you want efficiency, adaptability, and long-term performance, LVQ is the clear winner. But here's the real question. Where does LVQ actually get used in the real world? What kind of problems is it solving right now? In the next slide, we're diving into real-world applications, and trust me, some of these might surprise you. Let's go. All right, now that we know why LVQ is so powerful, let's talk about where it's actually being used. Because LVQ isn't just some academic concept, it's out in the real world, making real impact. From detecting fraud to medical diagnosis, this algorithm is quietly working behind the scenes in some of the most critical industries. Let's break it down. First up, image recognition. Ever wonder how facial recognition software knows who you are? LVQ plays a key role in classifying images based on pixel patterns. Instead of memorizing every single image like KNN, LVQ learns the important features, eyes, nose shape, facial symmetry, and builds a compact, efficient model for identification. This means faster recognition and lower storage costs, which is why LVQ is often used in biometric security systems. Now let's talk speech recognition. Have you ever used voice commands with your phone or smart speaker? LVQ helps classify audio patterns, distinguishing between different phonemes, accents, and even background noise. Unlike KNN, which would need to store huge amounts of training data, LVQ learns to represent sounds with fewer prototypes, making voice assistants faster and more responsive. Then there's medical diagnosis. Imagine a system that can help doctors detect diseases faster by analyzing patient data. LVQ is used in tumor classification, heart disease detection, and even genetic analysis. Why? Because medical data is often messy, high-dimensional, and full of outliers. LVQ filters out the noise and focuses on the key indicators that differentiate diseases, helping doctors make more accurate diagnoses with less computational effort. And what about finance? Banks and financial institutions use LVQ for fraud detection and risk assessment. Instead of checking every single transaction like KNN, LVQ identifies patterns of fraudulent activity, things like suspicious spending behavior, unusual transaction locations, or rapid money transfers. By constantly adapting to new fraud techniques, LVQ helps keep transactions secure and reliable. Even in stock market prediction, LVQ plays a role. Traders and analysts use it to classify historical stock trends, predicting whether a stock is likely to rise or fall. Instead of memorizing the entire market history, LVQ focuses on the most relevant factors, price movement patterns, volatility, and volume trends, allowing for faster, more accurate trading decisions. And it doesn't stop there. LVQ is also used in spam detection, customer segmentation, industrial automation, and even self-driving cars. Essentially, wherever there's classification happening with large, noisy data sets, LVQ can step in and streamline the process. But here's the thing. LVQ isn't magic. It needs fine-tuning to get the best results. So how do we train an LVQ model specifically for these applications? What steps do we need to take to optimize its performance? That's exactly what we're going to cover in the next slide. Stick around, because this is where we turn LVQ from cool theory into real working models. All right, let's zoom in literally on how LVQ powers image recognition. Whether it's facial recognition, object detection, or medical imaging, LVQ is helping computers see and understand the world in ways that were once science fiction. And the best part? It does it smarter and faster than traditional methods. Imagine you're building a facial recognition system. You could go the KNN route, where the system memorizes every single face it's ever seen and tries to match new ones by brute force. But that's ridiculously inefficient. With every new face added, KNN gets slower and hungrier for memory. It's like trying to recognize a friend in a crowd by comparing them to every person you've ever met. That's not how humans do it, and it's not how LVQ works either. Instead, LVQ learns the essential features of a face, the eye shape, nose structure, jawline, and other key elements, and represents them with a small set of optimized prototypes. So when a new face comes in, LVQ doesn't check every stored image. It just compares the new face to its learned representative vectors. The result? Way faster and way more memory-efficient classification. And it's not just faces. LVQ is used in medical imaging to help detect tumors, fractures, and other abnormalities. Instead of scanning thousands of past X-rays every time, LVQ learns patterns of healthy and unhealthy tissue, making diagnoses much quicker and more reliable. LVQ is also found in industrial automation. Think of an assembly line where machines need to inspect products for defects. LVQ helps classify images of products, instantly recognizing whether something is defective or up to standard, reducing waste and improving efficiency. And here's where it gets even cooler. LVQ can be combined with other machine learning techniques, like convolutional neural networks, CNNs, to create hybrid models that enhance accuracy while keeping computational costs low. Instead of processing every pixel in an image, LVQ focuses on the most important regions, making it ideal for real-time applications like autonomous vehicles and security systems. All right, we've seen how LVQ makes image recognition smarter and faster, but now let's talk about something even more impressive. Teaching machines to understand speech, whether it's your phone responding to, "Hey Siri," your car following voice commands, or automated customer service systems, speech recognition is becoming an everyday part of our lives. And behind the scenes, LVQ is helping machines learn to listen and understand. Now let's take a step back. How do humans recognize speech? If someone says your name in a crowded room, you instantly recognize it, even if there's background noise, different accents, or people talking over each other. That's because your brain doesn't memorize every single word you've ever heard. It learns patterns, recognizes familiar sounds, and ignores irrelevant noise. That's exactly what LVQ does for speech recognition. Traditional speech recognition models like KNN rely on storing huge amounts of speech data and comparing new sounds to everything they've memorized. But there's a problem. Spoken language is messy. People have different accents, speaking speeds, background noise, and even emotional tones. If a model just memorizes words without learning the underlying patterns, it's going to struggle. Think about how kids learn to talk. They don't just memorize words one by one. They recognize phonemes, the smallest units of sound, and combine them into words. LVQ works the same way. Instead of memorizing every possible pronunciation, it learns the key sound patterns that define words. This makes it way more efficient and adaptable than KNN. Here's how LVQ actually classifies speech. First, an audio signal is converted into a numerical representation, usually with techniques like mel-frequency cepstral coefficients, which transform sound waves into a format that machines can analyze. Then, LVQ breaks speech into smaller patterns, identifying the most relevant features like tone, pitch, and speed. Just like a human recognizes a friend's voice without needing to hear the full sentence, LVQ finds the best matching prototype vectors for each word or phoneme. Once the best matching unit is identified, LVQ adjusts its representative vectors over time. If the classification was correct, it moves the prototype closer. If it was wrong, it adjusts away, constantly fine-tuning itself for better accuracy. Because LVQ focuses on key sound features instead of memorizing everything, it has some huge advantages over traditional models. It's resistant to background noise, meaning it can pick out important speech patterns even in a noisy environment. It adapts to different accents by generalizing across pronunciations instead of locking onto one rigid definition of how words should sound. And it works in real time, keeping classification fast and scalable without slowing down as the dataset grows. That's why LVQ is widely used in virtual assistants like Siri and Alexa, in voice authentication systems for security, and even in medical applications where it helps detect early signs of neurological diseases like Parkinson's by analyzing speech irregularities. The future of LVQ in speech recognition is exciting. Researchers are finding ways to combine it with deep learning for even better natural language understanding. Emotion detection is another frontier where LVQ could help machines recognize not just words, but the emotions behind them, whether someone is happy, frustrated, or nervous, just by analyzing their voice patterns. But here's the big question. If LVQ is helping computers hear and understand, can it also help them diagnose diseases just by analyzing patient data? The answer is yes. In the next slide, we're diving into LVQ in medical diagnosis. And trust me, this one is mind-blowing. Imagine walking into a doctor's office, and instead of waiting weeks for test results, a machine learning model instantly analyzes your medical data and gives a highly accurate diagnosis. That's not science fiction. It's already happening, and LVQ is playing a key role in making medical diagnosis faster, smarter, and more reliable. Medical data is notoriously complex. It's full of inconsistencies, missing values, and noise. Patients with the same condition might have completely different symptoms, while others with similar symptoms might have entirely different diseases. Traditional classification models struggle with this kind of variability. KNN, for example, requires storing massive amounts of patient records and comparing new cases to every past diagnosis. That's slow, inefficient, and not practical when dealing with real-time medical decisions. LVQ approaches the problem differently. Instead of memorizing every past case, it learns representative patterns in the data. It identifies what a typical case of a disease looks like by refining prototype vectors over time. So when a new patient comes in, LVQ doesn't have to search through thousands of past records. It simply finds the closest representative vector and makes a classification instantly. That's why LVQ is used in cancer detection, heart disease diagnosis, and even genetic analysis. Take tumor classification as an example. When analyzing medical images, LVQ helps separate benign from malignant tumors by learning the key features that differentiate them, things like shape, texture, and density. Instead of relying on a doctor's subjective judgment, LVQ provides an objective, data-driven classification. The same applies to heart disease detection. By analyzing patient records, ECG patterns, and lifestyle factors, LVQ can predict the likelihood of heart conditions before symptoms even appear, giving doctors a crucial head start in prevention. But LVQ isn't just useful in structured medical data. It's also being applied in speech-based diagnosis, detecting neurological disorders like Parkinson's and Alzheimer's by analyzing subtle changes in a patient's voice. These diseases affect speech patterns long before other symptoms show up, meaning LVQ-powered tools could help with early diagnosis and intervention. What makes LVQ particularly valuable in medicine is its adaptability. Unlike many machine learning models that require clean, perfectly structured data, LVQ can handle messy real-world datasets full of missing values and inconsistencies. It learns what really matters in the data while filtering out noise, making it incredibly useful in environments where no two patients are exactly alike. The impact of LVQ in medical AI is just beginning. Researchers are working on hybrid models that combine LVQ with deep learning for even more accurate and explainable medical predictions. Soon, we could see LVQ being used in personal health monitoring devices, predicting potential illnesses from wearable sensor data before a person even feels sick. But making sure an LVQ model works well in medicine or any real-world application requires careful evaluation. How do we know if the model is truly accurate? What metrics do we use to measure its performance? And how can we fine-tune it to minimize errors? That's exactly what we'll cover in the next slide. This is where things get scientific. So LVQ is being used in critical real-world applications like medical diagnosis, speech recognition, and financial fraud detection. But here's the million-dollar question. How do we know if an LVQ model is actually performing well? Because let's be honest, in fields like healthcare or finance, a misclassification isn't just a small mistake. It could mean misdiagnosing a disease or approving a fraudulent transaction. That's why model evaluation is absolutely crucial. The first thing we need to look at is accuracy. How often does the model classify data correctly? If LVQ is predicting diseases, we want to know how often it gets the diagnosis right. But accuracy alone isn't enough. Imagine a medical model that predicts no disease for every patient. If 95% of patients are actually healthy, the model would have 95% accuracy, but it would be completely useless because it misses all the real cases. That's why we need to go deeper. Instead of just accuracy, we look at precision and recall. Precision tells us how many of the positive predictions were actually correct. In fraud detection, high precision means that when the model flags a transaction as fraud, it's almost always right, so customers don't get blocked unfairly. Recall, on the other hand, measures how many actual fraud cases were caught. A model with high recall detects almost all fraudulent transactions. But if precision is low, it might also flag too many false alarms. The key is finding the right balance between precision and recall, depending on the use case. Then there's the confusion matrix, which sounds complicated, but is actually a simple tool to visualize model performance. It breaks predictions down into true positives, true negatives, and false negatives. A medical diagnosis model, for example, should aim to have as few false negatives as possible, because missing a real disease is far worse than incorrectly flagging a healthy patient for further testing. Another important metric is the F1 score, which combines precision and recall into a single number. It's especially useful when working with imbalanced datasets, where one class is much rarer than the other. In fraud detection, for instance, actual fraud cases might only make up 0.1% of transactions, so just looking at accuracy would be misleading. The F1 score ensures the model isn't just performing well on the majority class while failing to detect rare but important cases. But here's the tricky part. LVQ's performance is highly dependent on how well it's trained. The number of prototype vectors, the learning rate, and the way we handle noisy data all impact its results. That's why cross-validation is often used, where the dataset is split into different parts to ensure the model generalizes well and isn't just memorizing patterns from the training set. So now we know how to measure LVQ's success. But what if the results aren't as good as we want? How do we improve the model, fine-tune its learning, and make it even more accurate? That's exactly what we'll cover in the next slide. This is where we go from good models to great ones. All right, so we know how to evaluate an LVQ model, but what if the results aren't where we need them to be? What if the accuracy isn't high enough, or the model struggles with complex patterns? The good news is that LVQ isn't just a set it and forget it algorithm. It can be fine-tuned and optimized to perform at its best. And today, we're going to break down exactly how to do that. First things first, optimizing the number of prototype vectors. If we use too few, the model oversimplifies the data, missing important patterns and leading to misclassifications. If we use too many, the model becomes too complex, slowing down training and potentially overfitting. The trick is to find the sweet spot, often through experimentation and cross-validation. Think of it like tuning a musical instrument. Too tight or too loose and it sounds off. Just the right tension and everything harmonizes perfectly. Next up, adjusting the learning rate. We already talked about learning rate decay, but finding the right learning rate from the start is just as important. If the learning rate is too high, LVQ updates the prototype vectors too aggressively, leading to unstable learning. If it's too low, The model learns too slowly and never fully adapts. A great strategy is to start with a higher learning rate and gradually decrease it over time, allowing for quick early adjustments and fine-tuned precision later on. Now let's talk about distance metrics. By default, LVQ uses Euclidean distance to determine the closest prototype vector, but sometimes Euclidean distance isn't the best choice, especially for high-dimensional data. Alternative metrics like Manhattan distance or Mahalanobis distance can sometimes improve performance depending on the structure of the dataset. Imagine trying to measure the distance between two cities. Do you go in a straight line, Euclidean, follow a grid of streets, Manhattan, or account for terrain and road conditions, Mahalanobis? Choosing the right approach makes all the difference. Another key strategy is dimensionality reduction. High-dimensional datasets can make LVQ struggle because distance calculations become less meaningful as the number of features grows. Techniques like principal component analysis, PCA, or TSNE can help by reducing the dataset to its most important features, making LVQ faster and more effective. It's like clearing out unnecessary clutter from a workspace. You end up focusing only on what really matters. We also need to consider handling noisy data. Real-world datasets often contain errors, outliers, and irrelevant features that can throw LVQ off. A great solution is data pre-processing, removing extreme outliers, normalizing values, and selecting the most important features before training. LVQ thrives when it's given clean, high-quality data, so feeding it the right information is crucial. Finally, one of the most powerful ways to improve LVQ is to combine it with other models. Hybrid approaches like using LVQ with neural networks or combining it with deep learning for feature extraction can enhance its accuracy while keeping classification fast and efficient. This is especially useful in complex problems like image and speech recognition, where LVQ alone might struggle with raw data, but excels when used alongside deep learning. So now we know how to make LVQ perform at its absolute best. But what if we're dealing with huge datasets with hundreds or even thousands of features? That's where the real challenge begins. In the next slide, we'll explore how LVQ handles high-dimensional data and what we can do to keep it running efficiently, even when faced with massive, complex datasets. Let's dive in. Let's talk about one of the biggest challenges in machine learning, high-dimensional data. As datasets grow in size and complexity, models like LVQ can start to struggle, making distance calculations less reliable and slowing down classification. But don't worry, there's a way to fix this, and it all comes down to dimensionality reduction. Think about it like this. Imagine you're trying to find a book in a giant library. If the books were perfectly organized by genre, author, and subject, you'd find what you need in seconds. But if everything was scattered across random shelves, the more books there are, the harder it gets to find anything. That's exactly what happens in high-dimensional spaces. As the number of features increases, the relationships between data points become less meaningful, making classification harder. This is known as the curse of dimensionality. LVQ, like many other distance-based models, suffers from this problem. When there are too many dimensions, the distance between points starts losing its effectiveness. Everything seems equally far apart, and classification becomes unreliable. If we feed LVQ too many irrelevant or redundant features, we're making it work harder for no real gain. The solution? Dimensionality reduction techniques, methods that strip away the noise and focus only on the features that actually matter. One of the most popular techniques is principal component analysis, PCA. PCA finds the most important patterns in the data, transforming high-dimensional data into a smaller set of meaningful components while preserving as much information as possible. It's like reducing a massive spreadsheet of numbers into just a few key statistics that summarize everything. Another powerful approach is T-distributed stochastic neighbor embedding, TSNE. Unlike PCA, which focuses on variance, TSNE is great for visualizing high-dimensional data by mapping it into a low-dimensional space while preserving relationships between points. It's perfect for spotting hidden clusters and patterns in complex datasets. Linear discriminant analysis, LDA, is another technique specifically designed for supervised learning problems like LVQ. Instead of just reducing dimensions blindly, LDA focuses on maximizing class separability, making it an excellent choice for classification tasks. The best part? Dimensionality reduction doesn't just make LVQ more accurate, it also makes it faster. With fewer dimensions to process, LVQ trains more efficiently, classifies data quicker, and avoids unnecessary complexity. It's like clearing out distractions from your workspace so you can focus on what truly matters. And here's where things get really interesting. Dimensionality reduction isn't just useful for classification. It also plays a huge role in feature selection, data visualization, and even improving generalization, helping LVQ perform well even with limited training data. So, what's the takeaway? If you're working with big, complex datasets, don't just throw everything into LVQ and hope for the best. Instead, reduce the dimensions, clean up the data, and focus only on the most important features. The result? A leaner, faster, and more accurate LVQ model. But what if we're dealing with even more extreme datasets, thousands of features, complex relationships, and messy, real-world data? That's where things get even trickier. In the next slide, we'll explore how LVQ handles high-dimensional spaces and what strategies we can use to keep performance sharp even in the most challenging scenarios. Let's go! All right, we've talked about dimensionality reduction and why it's crucial for LVQ, but what happens when we're dealing with massive datasets with thousands of features? This is where things get tricky. High-dimensional data isn't just big, it's complex, difficult to navigate, and often full of irrelevant information. If we don't handle it properly, LVQ can slow down, lose accuracy, and struggle to make meaningful classifications. But don't worry, because there are strategies to keep LVQ running smoothly, even in the most challenging data environments. Let's start with the biggest problem, the curse of dimensionality. As the number of features increases, the distance between data points becomes less meaningful. Imagine trying to measure similarity between two people based on just their favorite color and music genre. It's relatively simple. But now imagine you're using 1,000 different traits, including their favorite food, shoe size, birth month, and how often they drink coffee. At some point, the noise starts overpowering the real patterns, making it harder for LVQ to separate different classes effectively. Another challenge, LVQ needs more representative vectors in high-dimensional spaces. If the data set has too many complex features, a small number of prototypes won't be enough to fully capture all the variations. The result? Lower accuracy, slower training, and more misclassifications. The more dimensions we have, the more prototype vectors we might need, leading to higher computational costs. So how do we fix this? First, we need feature selection. Instead of feeding LVQ every single feature available, we need to choose only the most relevant ones. This can be done using methods like mutual information, recursive feature elimination, or domain knowledge to keep only the features that actually contribute to classification. Think of it like packing for a trip. You don't take everything in your closet, just the essentials. Next, we can apply dimensionality reduction techniques like PCA, TSNE, or LDA, as we discussed in the last slide. These techniques help compress the data while keeping the most important information, making classification much more efficient. Another approach is adaptive vector pruning, where LVQ dynamically adjusts the number of prototype vectors based on the dataset's complexity. Instead of keeping too many or too few, it finds the right balance. enough to capture important patterns, but not so many that it slows down performance. And finally, hybrid models can help LVQ thrive in high-dimensional spaces. Instead of relying solely on LVQ, we can combine it with deep learning or neural networks to extract features before feeding them into LVQ for classification. This way, LVQ only works with clean, structured, and meaningful data, making it much faster and more accurate. So, what's the bottom line? LVQ can absolutely handle high-dimensional data, but only if we clean it up, reduce complexity, and optimize feature selection. Otherwise, we risk drowning in an ocean of useless information where classification becomes slow, inefficient, and unreliable. But here's an interesting thought. LVQ itself isn't just a single algorithm. There are actually different versions of LVQ, each designed for different types of problems. Some versions handle noise better, some work better in high-dimensional spaces, and others are built for ultra-fast classification. In the next slide, we'll explore the different LVQ algorithm variants and when to use each one. This is where LVQ gets even more powerful. Let's dive in. So we know that LVQ is powerful, adaptable, and efficient. But did you know that there isn't just one version of LVQ? That's right. LVQ actually comes in different flavors, each fine-tuned to handle specific challenges like noisy data, high-dimensional spaces, and complex decision boundaries. Think of it like different models of the same car. Some are built for speed, some for off-roading, and some for luxury. Today, we're diving into the three major LVQ variants: LVQ1, LVQ2, and LVQ3, and figuring out which one works best for different scenarios. Let's start with LVQ1, the original, the classic, the simplest form of LVQ. This version follows the standard winner-takes-all approach, where the best matching unit, BMU, is updated based on whether it correctly classifies an input or not. If the classification is correct, the prototype vector moves closer to the input. If it's wrong, the vector moves away. It's straightforward, easy to implement, and works well on clean, well-separated datasets. But here's the problem. LVQ1 struggles with overlapping classes. If two classes have fuzzy boundaries, LVQ1 might not handle them well, leading to lower accuracy in complex datasets. That's where LVQ2 comes in. LVQ2 adds a second-best matching unit, SBMU, into the equation. Instead of just adjusting the winning prototype, LVQ2 also looks at the second closest prototype. If the input falls between two class boundaries, both vectors are updated, one moves closer and the other moves away, helping to refine decision regions. This makes LVQ2 much better at handling multi-class classification problems, where boundaries between classes aren't always clear-cut. It's especially useful when working with noisy datasets or situations where similar-looking inputs belong to different categories. And then we have LVQ3, which takes things up a notch by introducing adaptive learning rates and more flexible updates. LVQ3 still uses the second best matching unit like LVQ2, but it also adjusts the learning process based on how confident the model is in its classification. This makes LVQ3 more stable over time, reducing the risk of misclassifications and making it more robust to noise and outliers. It's ideal for datasets that are messy, overlapping, or constantly changing. If LVQ1 is like a sharp but inflexible decision maker, and LVQ2 is a balanced, strategic thinker, then LVQ3 is the experienced leader who knows when to make big moves and when to hold back. So which one should you use? If you're dealing with simple, well-separated data, LVQ1 works just fine. If your data has fuzzy class boundaries, LVQ2 is the better choice. And if your dataset is noisy, constantly evolving, or highly imbalanced, LVQ3 is your best bet. But what if none of these are enough? What if you need real-time classification, where LVQ has to work at lightning speed in environments like autonomous driving, robotics, or fraud detection? That's where LVQ in real-time systems comes into play. And in the next slide, we're going to see how LVQ is pushing the boundaries of AI speed and efficiency. This is where things get really exciting. Let's go. All right, we've seen how LVQ works in standard classification tasks, but what happens when we need instant decisions, on-the-fly learning, and extreme efficiency? That's where LVQ in real-time systems comes in, whether it's powering autonomous vehicles, industrial automation, fraud detection, or live speech processing. LVQ can be fine-tuned to work in environments where every millisecond counts. Let's start with one of the most exciting applications, self-driving cars. Imagine an autonomous vehicle navigating through a busy city. It needs to classify objects, cars, pedestrians, traffic signs in real time, making split-second decisions to avoid accidents. Traditional models like KNN would be way too slow, as they'd have to scan an entire dataset for every single classification. But LVQ? Since it only works with a small set of representative vectors, it can instantly recognize objects and react accordingly. And it's not just vehicles. Industrial robots use LVQ to classify parts, detect manufacturing defects, and even adjust their movements dynamically based on new inputs. In a fast-paced factory setting, there's no time for slow computations. Machines need to adapt and refine their decisions continuously. LVQ's ability to update representative vectors on the fly makes it ideal for real-time quality control and automation. Let's talk fraud detection. Banks and financial institutions process millions of transactions per second. Spotting fraudulent activity in real time is crucial to prevent financial losses. LVQ helps by learning patterns of fraudulent behavior, detecting unusual spending habits, high-risk locations, and suspicious transactions instantly. And because LVQ continuously adjusts its representative vectors, it can adapt to new fraud techniques without needing to store and compare billions of past transactions. Then there's real-time speech recognition. When you talk to a virtual assistant, it needs to understand your words immediately, not after searching through a massive dataset. LVQ speeds up the process by recognizing phonemes and speech patterns efficiently, allowing smart devices to respond instantly instead of lagging behind in conversation. This makes it perfect for live transcription, real-time translation, and interactive AI assistance. But here's the challenge. LVQ wasn't originally designed for real-time use, so how do we make it fast enough? The trick lies in vector reduction and parallel processing. By carefully selecting only the most essential prototype vectors, LVQ can work with smaller datasets without losing accuracy. And when combined with parallel computing techniques, where multiple LVQ models run simultaneously on different processors, classification speeds can be boosted even further. The future of LVQ and real-time AI is incredibly promising. From real-time medical monitoring that detects irregular heartbeats instantly, to cybersecurity systems that identify hacking attempts before they cause damage, LVQ is proving that fast, adaptive, and efficient machine learning is possible. But here's the big question. What happens when LVQ overfits and starts making mistakes? Can we prevent it from memorizing noise and ensure it generalizes well to new data? That's exactly what we'll tackle in the next slide, where we break down LVQ and overfitting, because even the best models need to be kept in check. Let's go. So we've seen how LVQ can be lightning fast in real-time systems, but now we need to talk about a critical issue, overfitting. If you've ever worked with machine learning, you know that overfitting is like that one friend who remembers every little detail but completely misses the bigger picture. It happens when a model learns too much from the training data, memorizing noise and outliers instead of recognizing real patterns. And guess what? LVQ isn't immune to this problem. So how does overfitting happen in LVQ? And since LVQ adjusts its representative vectors based on the training data, it can sometimes become too specific, shifting its prototypes to fit every little variation rather than generalizing. This is especially problematic when training data is small, noisy, or unbalanced. Imagine teaching a kid to recognize dogs, but they've only seen one specific breed. The moment they see a different kind of dog, they're confused. That's what happens when LVQ overfits. It performs perfectly on training data but struggles with anything new. One of the biggest culprits, too many prototype vectors. If we use too many, LVQ starts memorizing every detail instead of learning general class boundaries. This makes it highly sensitive to noise, leading to bad predictions on unseen data. On the flip side, too few prototype vectors can cause underfitting, where LVQ oversimplifies patterns and fails to capture important variations. Another issue is a poorly tuned learning rate. If the learning rate is too high, LVQ jumps around too aggressively, failing to settle into an optimal state. If it's too low, it gets stuck in local patterns and might overfit specific clusters of training data instead of generalizing. So, how do we prevent overfitting? The first and most effective approach is cross-validation. Instead of training on just one set of data, we split the data set into multiple parts and rotate them through training and testing. This ensures LVQ isn't just memorizing one dataset, but is actually learning patterns that generalize across different samples. Next, regularization techniques help control overfitting. One powerful method is weight decay, which gradually reduces how much LVQ updates its prototype vectors over time. This prevents it from making excessive adjustments to fit noise, forcing it to stick to broader, more reliable patterns. Another trick? Early stopping. Instead of training LVQ until it perfectly classifies every data point, we monitor its performance on a validation set. The moment it starts improving on training data but worsening on validation data, we stop training, ensuring it doesn't memorize noise but instead maintains generalization. Dimensionality reduction also plays a huge role. If we remove irrelevant or redundant features, LVQ focuses only on the most meaningful information, reducing the risk of overfitting to useless details. It's like clearing out junk from a workspace. Fewer distractions, better focus. And finally, reducing prototype vectors dynamically can make a huge difference. Instead of using a fixed number of representative vectors, we can prune unnecessary ones, keeping only the most critical for classification. This keeps LVQ lean and prevents it from overfitting by forcing it to generalize rather than memorize. So, what's the takeaway? Overfitting can be a challenge, but with cross-validation, regularization, learning rate control, and dimensionality reduction, LVQ can maintain its power without falling into the trap of memorization. But let's take this one step further. What does the future of LVQ look like? How will it evolve to handle even more complex data, integrate with deep learning, and push the boundaries of AI? That's exactly what we'll explore in the next slide, where we dive into the future of LVQ research. And trust me, this is where things get really exciting. We've explored how LVQ works, where it's used, and how to fine-tune it, but now let's take a step into the future. Where is LVQ headed? How will it evolve to meet the challenges of tomorrow's AI? And what breakthroughs could make LVQ even more powerful? The answers are closer than you think, and some of them might surprise you. One of the most exciting areas of LVQ research is its integration with deep learning. Right now, deep learning models like neural networks excel at feature extraction, but they often require huge datasets and massive computing power. LVQ, on the other hand, is efficient and interpretable. Imagine combining the two, using deep learning to extract meaningful, high-level features, and LVQ to handle fast, memory-efficient classification. This hybrid approach is already being tested in medical AI, autonomous systems, and advanced image recognition, and the results look promising. Another area of innovation, LVQ in reinforcement learning. Today, reinforcement learning powers self-driving cars, robotic automation, and game-playing AI. But these models often struggle with efficient memory usage and fast decision-making. LVQ could help by acting as a compact memory system, reducing the need for massive data storage while still allowing models to adapt dynamically. Some researchers are exploring how LVQ could replace traditional memory-heavy Q learning models, making reinforcement learning faster and more scalable. And then there's explainable AI XAI. One of the biggest criticisms of deep learning is that it works like a black box. It makes decisions, but we don't always know why. LVQ, on the other hand, is highly interpretable. Since it uses prototype vectors, it's easier to visualize how and why it classifies data the way it does. This is a huge advantage in fields like healthcare and finance, where AI decisions need to be transparent and justifiable. Expect to see LVQ playing a bigger role in AI systems that require human trust and regulatory approval. Another breakthrough on the horizon: LVQ for real-time streaming data. Most LVQ models are trained on static datasets, but real-world data is constantly changing. Think financial markets, cybersecurity threats, and IoT sensor data. Researchers are developing adaptive LVQ models that can update prototype vectors in real time, making them perfect for environments where data never stops flowing. And let's not forget edge computing and embedded AI. As AI moves out of massive data centers and into small devices like smartphones, drones, and IoT sensors, memory efficiency becomes critical. LVQ's ability to classify data with minimal storage makes it an ideal candidate for low-power, high-speed AI applications. Imagine a tiny LVQ-powered chip inside a smartwatch detecting irregular heartbeats on the fly without needing cloud processing. That's the kind of AI that could change lives. LVQ is also making waves in hybrid machine learning models, combining with techniques like support vector machines, SVMs, decision trees, and clustering algorithms to create more flexible, high-performance AI systems. These hybrid models are being tested in bioinformatics, fraud detection, and even climate modeling, showing that LVQ still has plenty of room to grow. So what's next? Expect to see LVQ getting faster, smarter, and more integrated with cutting-edge AI techniques. It's moving beyond traditional classification and into the world of real-time decision-making, deep learning partnerships, and scalable AI solutions. As researchers push the boundaries, we're looking at a future where LVQ isn't just a tool, it's a core component of next-generation AI systems. But before we wrap up, let's bring everything together. In the next slide, we're going to summarize everything we've learned about LVQ, the key takeaways, why it matters, and how it's shaping the future of machine learning. Let's finish strong. This is the end, and we've covered a lot about learning vector quantization, how it works, where it's used, its advantages, challenges, optimizations, and even its future. But let's take a step back and summarize everything into the key takeaways you need to remember. LVQ is a powerful, supervised machine learning algorithm that classifies data by using representative prototype vectors instead of storing the entire dataset. Unlike KNN, which memorizes every single data point, LVQ learns and refines patterns, making it faster, more memory efficient, and adaptable for real-world applications. It all starts with finding the best matching unit, BMU, the prototype vector that's closest to the input. LVQ then adjusts the BMU, moving it closer to correctly classified points and away from misclassified ones. This iterative learning process ensures that the model continuously improves over time, refining its ability to classify data accurately. One of LVQ's biggest advantages is its efficiency. Since it only stores a few key prototype vectors, it requires far less memory than KNN, making it a great choice for large datasets, embedded systems, and real-time applications. It's also highly interpretable, allowing us to see exactly how it makes decisions, a major advantage over black box models like deep learning. But LVQ isn't perfect. It struggles with high-dimensional data requiring dimensionality reduction techniques like PCA or TSNE to improve performance. It also needs careful tuning, including selecting the right number of prototype vectors, adjusting the learning rate, and using techniques like cross-validation to prevent overfitting. LVQ has evolved into multiple variants, including LVQ1, LVQ2, and LVQ3, each designed to handle different challenges like overlapping classes, noisy data, and adaptive learning rates. In recent years, LVQ has also been integrated into hybrid AI models, deep learning frameworks, and reinforcement learning systems, expanding its capabilities even further. And let's not forget the real-world impact. LVQ is actively used in image and speech recognition, medical diagnosis, fraud detection, robotics, and autonomous systems. It's making AI smarter, faster, and more efficient, proving that machine learning doesn't always have to rely on massive datasets and complex neural networks. Looking forward, LVQ is becoming even more adaptive and scalable, with researchers developing real-time streaming models, edge computing solutions, and hybrid machine learning architectures. It's playing a growing role in the future of explainable AI, reinforcement learning, and embedded AI systems. So, what's the big takeaway? LVQ is not just a classification algorithm. It's a machine learning powerhouse that balances speed, efficiency, and adaptability. Whether you're working on real-time AI, low memory devices, or complex classification problems, LVQ is a tool worth mastering. And that's a wrap. If you found this insightful, don't forget to share your thoughts, ask questions, or even experiment with LVQ yourself. The more we explore and refine these algorithms, the closer we get to building AI that's truly intelligent, efficient, and scalable. Keep learning, keep innovating, and I'll see you in the next deep dive.